Robert Steinke. Yep.
Well, okay. I think we can get started. We are a bit behind the schedule, but should be okay. So we'll start this session, and we have very interesting talks. And the first one is about ADHydro from Robert Steinke.
All right, so I'm Robert Steinke. I'm from the University of Wyoming, and I'm going to talk about ADHydro. It's our application that we're using Charm++ for. ADHydro is a hydrology simulation, so we simulate watersheds. After the raindrop or the snowflake hits the ground, where does that water go? That's really the question we're answering. So, of course, our simulation is going to be generally useful, but we have one kind of specific use case that we've, targeted the project towards, and that is to simulate the upper Colorado River on the Yellowstone supercomputer. So Yellowstone is a computer that is in Cheyenne, Wyoming. It's owned jointly by the National Center for Atmospheric Research and the University of Wyoming. We at the university own about 20% of it. And you can see there, that's the outline of the upper Colorado watershed. That's actually not a polygon. That is lines. Those are all of the streams. But the stream network is so dense at that scale, it basically covers everything. So the upper Colorado watershed, almost 300,000 square kilometers of area, almost 500,000 linear kilometers of streams. And you may have heard that the West is kind of in a bad situation in terms of water. There are some really big questions that have real societal impacts about our little watershed. And Yellowstone, 1.5 peak petaflops. I just looked at the list, and we've been going down the list over time. We're now down to 36th fastest. Okay, so there's two primary research questions we want to answer. First, how will climate and land use changes affect water availability? We want to be able to run decadal simulations with, wet, dry, and normal scenarios, and see kind of the risk of what's the chance of us getting below a certain amount of water input into Lake Powell. And Lake Powell is the bank account for the upper Colorado watershed states, which are Colorado, Wyoming, Utah, and New Mexico and Arizona have a little bit of it. And basically, the upper Colorado states have an agreement with the lower Colorado states. Within the upper Colorado, the states have agreements with each other, and then within each state, there's water management boards. So it's kind of like a hierarchy of bickering that goes on. And then the second thing that we want to ask is, how can we optimize water management, and how much water can we save? So, for example, there's a big question about if you change from flood irrigation, where you basically just open a gate and let water run out onto the field, to center pivot irrigation, those big circles where you have an arm that goes around to pivot sprinkling water. How does that affect return flows? Okay, so we know how much water we put onto the field, but that water soaks in. Some of it gets transpired into the air by the plants. Other water goes down to deep aquifers that we won't see for thousands of years. And other water flows laterally, and some of it maybe comes back out of a spring somewhere. How much do you get back? And do these two irrigation methods differ in how much return flow you get back? Because they want to get credit for that. The farmers say, well, okay, I used 10,000 acre-feet, but 2,000 of those acre-feet will eventually return to the Colorado River within a certain time span. I shouldn't be charged for that. And so we want to answer questions about this in a quantitative way. Additionally, we have another research goal that we kind of discovered over time, that we really want to explore high resolution from a capability-based point of view. So rather than asking how much resolution do we need to answer these two questions accurately, we have this brand spanking new supercomputer. How much resolution can we get And what will that resolution allow us to ask? So that's the kind of capability-driven approach. Okay, so we want to use high resolution. As I say, we've got almost 300,000 square kilometers of area, and our mesh elements can be as small as a half an acre. And we think that that is a level that will allow us to do things that haven't been done by large watershed scale simulations in the past. And we need variable resolution. There are a lot of areas in this watershed where, for the questions we're asking, nothing much interesting is happening. And so we want to use an unstructured mesh. We want to have less resolution in a lot of places. And we're planning on doing some experiments with offline mesh coarsening. So we start with a high resolution mesh, we run it, and then we coarsen that mesh and run it again and again at different levels of resolution to see how that affects the results. And then we want to do adaptive resolution. We've got temporal resolution adaptive, but we don't yet have adaptive mesh refined and implemented into the code, but that is a long-term goal. And that's the AD in ADHydro actually stands for adaptive. Okay, so we say that we're a multi-physics model, and in the hydrology community, there's a distinction between conceptual models and physical models. And a conceptual model is basically you think of the watershed as a set of resistors and capacitors, and you assign resistance and capacitance values, and you tweak those values until what comes out of your stream at the bottom of the watershed fits the historical data. That works, and it's fine at predicting things if what you're predicting is exactly the same as what's happened before. But if you ask about things like land use changes, if we clear-cut this forest, how does that change those values, those capacitor and resistor values? And there's no really good way to do that other than trying to fit new historical data after you've clear-cut the forest. Instead, we're a physical model. And that means that all of the parameters, all the inputs to our model are in theory testable in the lab. So you know the porosity, the conductivity of the soil, those kind of things are what we take in as inputs. We don't fit to historical data. You have a map, you have the soil types. We say in theory they're measurable in the lab because you have a limited resolution in your land surveys. That's probably the thing that's going to most limit our accuracy is that, okay, we have over this area, the soil type is sandy loam. Okay, but it's not totally uniform, but we've got to use a uniform value for that area because we just don't know any better. That's the highest resolution that the survey has to tell us what the soil type is. But we put these physical parameters into our model, and we run simulations of physical processes rather than a conceptual process that's just fit to historical data. Yeah, so currently our physical inputs are fixed in time. We don't have anything set up to have changes over time, but that is a long-term goal that you would. So right now our plan is basically to run different scenarios. You'd run scenario A with these parameters and then run scenario B with these parameters and see the differences. But one thing that would be neat is to have a city grow over time. And so land gets paved over time as the simulation runs. Yeah, that's not something we have yet. But it is a very interesting capability to have. Okay, so we're basically modeling multiple fairly independent physical processes. Okay, water hits the ground. Some of it evaporates, some of it soaks in, some of it runs off overland to a stream. These processes are largely physically independent just based upon the saturation, the water content and water pressure at each point. And we're designing the system as sort of a set of independent swappable modules with an API. So another thing that we want to be able to do with our code or want to be able to provide to the community is there are a lot of researchers who, I specialize in snowmelt, and I have a new way to model snowmelt. And so I would really like to test out my snowmelt model in a watershed model. So we can provide an existing watershed model, and there's a module for snowmelt, and you just write your snowmelt code to match our API, and we'll run our simulation with your snowmelt model. And then the water that comes out of the bottom of your snowpack goes into the ground, and we use all the rest of our physical models to determine what happens to it after that. So this idea of swappable independent physics modules is kind of a neat and interesting idea that we are implementing in our code. And there's another interesting wrinkle, is that part of our simulation is water management, which is based on decisions made by people and not on physics. And so it's been interesting to integrate that into a physics simulation. Our simulation is an explicit first-order simulation. It's not the most sophisticated numerical method, but we do worry about converging and conserving mass, and it also makes it a lot easier to have these independent swappable modules. It makes the API pretty clean and direct. So here's basically the overall architecture. We have these physics modules, are the rectangles around the edge. Snow melts, rain falls, it soaks in, some of it evaporates, the plants transpire water. And then you have water running off over the surface through channels like streams, running laterally as groundwater underground. And then we have a water management layer that kind of, magically takes water from here and puts it over there. And water management is things like reservoirs that release water and irrigation and just basically any humans moving water around. It can also be like diversions, transbasin diversions to another watershed. Okay, there was one more thing I wanted to say on this graph. So that oval in the middle that says state variables, well, that's where Charm++ fits in, right? So those state variables, you could imagine running this as a serial simulation where that's just like a big matrix or a bunch of objects. But we have those state variables distributed all over our parallel processor, and basically it's implemented as a bunch of char objects in Charm++. We did look at different ways of implementing it. We picked Charm++ because it gives us a lot of things for free. Partitioning, load balancing, and checkpointing were very valuable to us. It seemed like it would be a lot easier to overlap communication and computation than if we'd done it in MPI ourselves. And something that actually came out as we were working as an important feature of Charm++ is that it doesn't require you to really be an advanced C++ programmer in order to use Charm++. Our domain experts are hydrologists. They are not computer scientists. They don't want to use templates. They really, okay, they can write a class, but they'd rather not deal with a class hierarchy of inheritance. Charm++ kind of hides all that from you, and you have to do very little actual C++ code that isn't C code in order to make it work with Charm++. Okay, so at the Superhuman Conference at the Birds of a Feather workshop, I gave a presentation, and we had developed a version of the simulation that was essentially each mesh element was a separate char. And that was a useful thing to do. It was a useful step in sort of incrementally implementing this. It helped us understand how Charm++ works, and we learned a lot by doing it, but it didn't have the performance that we wanted. So lately, our more recent implementation work has been focused on two things. First of all, creating regions where a single char object would hold more than one mesh element. And second of all, heterogeneous time stepping, where not every element has to run at the same time step. The basic motivation for regions is that it reduces chair switching overhead, that one mesh element is just too small, and it gives overhead. And we've also been able to aggregate messages. We're not using TRAM, but I read up on TRAM, and I've got a lot of good ideas from it. We don't really need the topological routing component of TRAM. We don't really do kind of all-to-all communication ever. Each region just needs to talk to its neighbors. So the kind of rows and columns aggregation that TRAM does, we don't really need. But we do aggregate messages, and as a region, you know, loops over all of its elements, when an element sends a message, it really just hands the message to the region, and the region says, is this destination element is someone that I own? And if it is, it just delivers it immediately. And if it's not, it doesn't send a charm message immediately, it puts it in a vector. And we basically just have a vector of messages for each destination region. And so as you loop over all of your mesh elements, you can accumulate these messages in vectors, and then when you're done, when you're about to exit your entry method and release control back to the charm system, you just go to your vectors and send one charm message with all of the messages destined for that one region. And actually, it worked out really neat. So basically, a message is just a struct, and I have a pup bytes declaration on the struct, so that becomes immediately puppable. And then because of the pup-STL framework, a vector of those structs is also puppable. So I just send a charm++ message. Its one argument is a standard vector of my struct, and when it gets to the destination, all I do is loop over the elements of that struct and pretend that each one of them was received as a separate individual message. It really was easy. So that's all I'm going to say about regions. I'm going to talk a little more about heterogeneous time stepping now. And basically, it's a system, we decided on a system where neighbors agree on a flow rate and then an expiration time for that flow rate. And then the neighbors can each independently step forward at whatever time step they want, and they just keep that flow rate until they both hit the expiration time. And it's a kind of a 5-step algorithm. First, they calculate this nominal flow rate. And each pair of neighbors comes to an agreement about a flow rate and an expiration time. And in theory, these expiration times could be anything, but it's actually more efficient if we make them all expire at sort of integer divisible times so that multiple ones expire at the same time if they're close. And basically, the flow rate will not be recomputed until they hit that expiration time. Although in order to conserve water, we do have a step in the system where if an element's outflows add up to more water than it has, in that situation, we probably do want to scale the time step back a little bit, but at least for protection, we prevent more water from going out than the element has. It just scales back all of its outflows by, just linearly, based on how much water it has. And then the expiration time has to account for a couple things, both like the Courant number criteria of the water that's flowing right now, plus any possible shocks. So you could have a situation where this area is dry, there's really no water moving anywhere, the Courant number says your time step could be an hour, and yet a half hour from now, a rainstorm is going to start, so we've got to look ahead in the forcing file and say, let's not go beyond that. And then both neighbors agree to sync up at the expiration time and calculate it again. So this just imagine a triangular element, and these are my 3 neighbors, and I've calculated an expiration time with each of my 3 neighbors, and those times can be 3 different times. Then each element can select its own time step. And in practice, we're having each region select a time step, and the region runs the same time step for all elements in the region. All those elements are close to each other, and so they'd usually select similar time step anyways because the same weather conditions are going to be prevailing. But in theory, each element could select a separate time step from every other element. Okay, and so you see this element is selecting the time step. End time is equal to its shortest expiration time. And then I know what my flows are going to be until that time. I know how much water I have. I can send water outflows to my neighbors. And here is where we limit outflows to not be more than the amount of water that any element has. Okay, so if you imagine this first neighbor is water flowing from me to the neighbor, I will send him a message. The other 2 neighbors, maybe there's no flow, maybe the neighbors are flowing in towards me, I'm going to wait for messages from them. Okay, so that's the next step. Wait for those water messages to come in from your neighbors. And so, for example, here, I mean, this is a little hard to see, but you can see on the right-hand side, the rightmost neighbor sent all the water for my entire time step, but the middle neighbor has a time step shorter than me, so he only sent half of the water, or water for half of the time of our agreement. And so I still have to wait, and then when my neighbor calculates the second time step, he'll send the rest of the water, and now that I've gotten inflows of water until my time step expiration time, I can step my time forward. And that's basically step 5, advanced time. You just update your water and start again. And this algorithm is very nice. We've got a little proof that it can't possibly deadlock. It's guaranteed to conserve water. And if you look at the CI file, we've got basically structured dagger code that looks pretty much like this presentation. It's got step 1, get a message. Step 2, do this. Step 3. So it translates pretty directly into structured dagger code. Okay, so that's all I had. If there's any questions. Yeah, so the question is, where's the load imbalance coming from? So we don't have as much problem with load imbalance as we do with just communication partitioning. Now, there is going to be some issues of load imbalance from the heterogeneous time stepping. So areas that have more water need to use a shorter time step, and where the water is going to change over time based on where it's raining. So there is some load balancing for that, but primarily the issue is partitioning and just sort of convenience of the location transparent messaging helped our system.
Any other question? If not,
yeah.
Yeah.
Right, so the question is the performance of the region code sufficient? Well, we just really finished coding it, and we're kind of in debugging phase, so we don't have performance numbers for the latest version of the code yet. So I'll give you kind of what we do know. We've been running the non-region code, and with a certain number of cores on a certain size little test area, which would weakly scale up to the Upper Colorado on Yellowstone test case that we want. We're getting a speed factor, which is simulation time over real time of between 10 and 20. So we can simulate 10 hours in 1 hour. And what we'd really like to be is at least 100, which would be to simulate a year in 2 days. Or we'd ideally like to be at 1,000 to simulate decades of time. So going from, we expect that going to the region code will be able to get us at least close to 100. We're at 10 to 20 now. We're pretty confident we'll get to 100. And 1,000 is kind of our stretch goal. So we don't have any performance numbers yet, but we're optimistic we'll be able to meet what we hope to achieve. Right, so what codes can we compare with? The most widely used code to do this sort of thing is Geisha, and it's based on a raster grid. So there's really no way to run Geisha on watersheds as big as what we want to do. We will do some comparison with Geisha on smaller watersheds, but we haven't gotten that work done yet.
Okay, no more questions. So let's thank our speaker.